Hey everyone, welcome to The Explainer. Today, we're diving into something absolutely crucial. We're going to tackle a massive problem in software engineering, the very real danger of ambiguous software. And how are we going to solve it? By exploring the sheer mathematical elegance of the Z formal specification language. Let's get right to it.
Here's a quick look at our roadmap for today. We'll kick things off with what software specifications actually are, then shift gears into 3 different views of programs. From there, we'll introduce the Z language itself, break down the anatomy of Z schemas, walk through a library books example, and finally wrap up with schema inclusion and modularity.
Section 1. What are software specifications? The blueprint of reliable software.
Okay, let's dive right into this. Before we even touch the Z language, we've got to ask, what exactly is a specification? If you think about the root causes of major software failures, the bugs, the crashes, the massive system vulnerabilities, almost all of that chaos stems from developers either misunderstanding what the system was actually supposed to do or building something that was just logically flawed right from the start.
So to prevent those absolute disasters, a specification needs some very specific features. It's got to be correct, consistent, and complete. But honestly, most importantly, it has to be unambiguous, verifiable, understandable, expressive, and analyzable. I know that's a mouthful, but when a spec hits all of these marks, it leaves literally zero room for misinterpretation by the person actually writing the code.
Ultimately, you can think of a specification's role as an intermediate product in development. It's the absolute baseline for ensuring correctness. It acts as a rock-solid contractual agreement between the client with the idea and the developers building it. It's really the ultimate means of communicating ideas clearly so everyone's on the exact same page.
Section 2. 3 views of programs. Shifting our perspective.
To really grasp how formal specifications work, we have to change how we traditionally look at code. The first way we usually see programs is the instruction view. This is your standard, basic, sequential way of looking at things. It's like stepping through a recipe line by line. Load a variable, add 1 to it, store it. Just a predefined order of execution.
Then, we can zoom out a bit to the functional view. This abstracts the program and views it as sequential streams of data. Picture multiple inputs flowing into a central program block, which crunches the data and spits out sequential streams of output. It's all about what goes in and what comes out.
But here is the crucial point. The third perspective is the state-based view. Instead of fixating on individual instructions or data streams, we look at the whole system as a sequence of states, moving from an initial state to a final state. Understanding how a system transitions from one highly defined state to another, that is the exact conceptual bridge we need to understand the Z language.
Section 3. Introduction to Z language. Mathematical rigor in software.
All right, with that groundwork laid, let's introduce the star of today's explainer. Z, which is typically pronounced Zed, is a formal specification language with some serious academic pedigree. It was developed by Jean-Raymond Abrial over at Oxford University way back in 1974.
The defining feature of Zez is its intense mathematical rigor. Named after mathematicians Zermelo and Frankel, Zez is a strongly typed language based entirely on set theory and first-order predicate logic. This means we're using strict mathematical variables, sets like natural numbers, and logical operators. We're talking unary operators like not, connectors like and, or, and implies, plus first-order qualifiers like for all and there exists to define the exact unbreakable constraints of our software.
Section 4. Anatomy of Z schemas. Building blocks of Z.
So, to actually write out these mathematical constraints, Z uses a fundamental building block called a schema. The schema is how we define the state spaces and operations of our system, and it's visually and logically split right down the middle into 2 parts. The top half is the declarative or signature part. This is where you declare your variables and their types, basically saying, here is the data we're working with. The bottom half is the predicate part. That's where you define the logical constraints and invariants that apply to those variables, dictating exactly how they must mathematically behave.
Section 5. The library books example. Grounding the math in reality. Now, if all this sounds a little too abstract, let's ground it in reality. What's really fascinating here is how Z maps pure math to physical actions, like shelving a book. Looking at this library book schema, we're defining the complete state space for the status of books in a theoretical library. Let's break this down half by half.
Looking at the top half, our signature, we see how Z builds up data types to track our inventory. First, we declare books, in lib and checked out as power sets of the type books. Next up is lent2. We define this as a partial function connecting books to persons. Finally, we declare onShelf as another partial function, mapping books to shelves. We've essentially just laid out all the mathematical pieces on our board. Now moving to the bottom half, we get to the predicates. These are the unbreakable rules of our library. First rule, the books currently in the library, in lib, absolutely must equal the domain of the onShelf function. Second rule, the checked out books must equal the domain of the lent2 function. And finally, the master list of all books must be the union of inlib and checked out. Because of these rigid mathematical predicates, our library's inventory can never, ever be inconsistent. A book literally cannot just vanish. The math won't allow it.
Section 6. Schema Inclusion. Building massive systems incrementally.
That library schema is super effective, right? But to model massive, highly complex software applications, we need a way to snap these individual schemas together. And this brilliantly illustrates one of the coolest features of Z, schema inclusion. This allows developers to work entirely modularly. You just state the name of a referred schema inside the signature part of a new one. When you do that, Z automatically merges their signatures together and conjoins all their predicate rules. It's like building blocks.
If you're coming from a modern programming background, this quote from the source material is going to hit the nail on the head. The schema inclusion is a bit like the inheritance or include. It lets you build this massive, mathematically sound architecture by just stacking the rigorous rules of smaller, perfectly defined components.
We've seen how Z takes a vague idea and transforms it into a mathematically unbreakable contract. Knowing that software bugs can cost companies literally millions of dollars and sometimes even put safety at risk, I want to leave you with this thought. How might utilizing the rigorous mathematical blueprints of formal specifications change the way you approach your next big software project? Is it finally time to leave ambiguity behind for good? Thank you so much for joining me on this explainer, and we'll catch you next time.